Section: Introduction. In this section, we explore the capabilities of large language models, LLMs, and their complex nature, which often makes them difficult to understand. We question how these models develop reasoning skills, when they make errors, and what changes occur in each layer during training. This lack of clarity can lead to issues like the unintended generation of biased or harmful content, which complicates our ability to address these problems. We recognize that interpretable machine learning can either create models that are easy to understand or use methods that analyze models after they have been trained. While there have been significant advancements in interpreting static models, the dynamic training patterns of LLMs, particularly how gradients behave across different layers, remain less explored. Understanding these gradients is essential as they indicate how LLMs interact with training data. Recently, there has been an increase in methods focusing on specific layers of LLMs, such as the need for more low-rank adaptation, LoRA, in higher layers and identifying layers related to safety. However, current research primarily uses probing methods that assess model behavior by observing performance changes when layers are altered. While these studies have provided insights into how layers process information, they often do not reveal the gradients that drive learning. Therefore, we aim to advance this understanding by directly examining the layer-wise gradients in LLMs. Our study specifically looks at the gradients of LLMs after instruction tuning on instruction response pairs. Instead of fine-tuning, we analyze the gradients of 5 base LLMs and 5 instruction fine-tuned LLMs across various tasks, including math, common sense reasoning, and knowledge extraction. We also differentiate between correct and irrelevant responses, as well as fast and slow thinking, which relates to different reasoning paths. We focus on comparing the layer-wise gradients using their spectral properties, particularly in the projection layers for query, key, value, and output in transformer architectures. We measure the gradients using their nuclear norm, compare norms across layers, and assess how sensitive gradients are to different training data or initial models. These metrics help us understand training behaviors and provide insights for improving training strategies and model stability. Our main contribution is analyzing the gradient behaviors across different layers of LLMs through spectral analysis. We compare gradients from slow and fast thinking rationales when training various initial models with correct and irrelevant responses across different tasks. The differences in gradients reveal how these factors influence training dynamics and how sensitive LLM training is to them. Our findings uncover new patterns and insights that could enhance the stability and efficiency of LLM training. We observe that training LLMs for slow thinking leads to similar gradient norms across layers, while fast thinking results in larger gradients in earlier layers and significant differences across layers. The gradients from slow thinking help distinguish correct responses from irrelevant ones, whereas without a structured reasoning approach, the gradient patterns for both response types are similar. Additionally, instruction fine-tuned LLMs do not outperform pre-trained base LLMs in identifying incorrect reasoning paths. These observations from reasoning tasks do not apply to knowledge learning tasks, where simply increasing response length does not yield similar gradient patterns as slow thinking. In our methodology, we utilize common instruction tuning settings to investigate gradients for LLM fine-tuning. Each data sample consists of an instruction and its corresponding response. We focus on the gradients related to the attention mechanism, particularly in the query, key, value, and output projection layers. Given that LLMs have many attention layers, the gradient for each projection layer is a matrix corresponding to its weights. Due to the large number of layers and parameters, directly analyzing these matrices is impractical. Therefore, we employ singular value decomposition, SVD, to represent the characteristics of each layer's gradient, particularly its strength. SVD allows us to factor a matrix into components that reveal its structure. For our gradient matrix, we can decompose it into orthogonal matrices and a diagonal matrix of singular values. The nuclear norm, which is the sum of the singular values, reflects the sparsity of the spectrum and serves as a useful measure for understanding the matrix's properties. Section Summary. In this section, we explore the layer-wise gradients of large language models, LLMs, during instruction tuning, focusing on how these gradients vary across different tasks and reasoning types. Our analysis reveals distinct patterns in gradient behavior that inform training dynamics and model stability, particularly highlighting the differences between slow and fast thinking processes in LLMs. Section: Metrics of Gradient Difference. In this section, we focus on the metrics of gradient difference. Instead of examining the nuclear norm of each layer individually, we analyze the overall dynamic characteristics across all layers of the large language model, LLM. For simplicity, we represent the nuclear norm value of a specific metric across all layers as a curve, denoted as S_x. Visualizing these layer-wise curves is crucial for qualitatively understanding how gradients change across layers, but we also need quantitative analysis for deeper insights. To capture the fluctuation and scale of the gradient curve, we use the mean absolute difference, MAD, to represent it. We denote the MAD of the curve S_x as MAD_S_x, which we calculate based on the total number of layers in the LLM. MAD measures the average change between consecutive points, focusing on direct differences without considering direction. This makes it useful for identifying variability and local changes, which are often more significant than overall trends. We also compare pairs of curves across different layers using the layer-wise relative difference, ROD. For each layer, we calculate the ROD between two values, using one as a reference. It's important to keep the projection layer and layer index the same for meaningful comparisons. We investigate gradients for 10 models, including 5 base pre-trained models and their instruction-tuned versions. Our main illustrations will focus on the Qwen 2 to 1.5b model, while results for other models will be included in the appendix. Our datasets fall into 3 categories: math, common sense reasoning, and wiki knowledge. We use the math and common sense reasoning datasets to explore gradients when LLMs are fine-tuned for reasoning processes, and the wiki knowledge datasets for learning pure knowledge. Due to the time-consuming nature of gradient calculations, we randomly sample 500 data instances for each task for our experiments, as detailed in the accompanying table. More information about these datasets and examples can be found in the appendix. For math reasoning, we utilize datasets like Aqua, GSM-8K, and Math. Aqua presents options from A to E, GSM-8K provides resulting digits, and Math requires complete solutions, which can be seen as answers with reasoning paths. We focus on question types such as algebra, counting, and geometry, and we also use GPT-4o to obtain detailed reasoning paths. In the common sense reasoning category, we employ 4 datasets: Strategy QA, ECQA, Creek, and SenseMaking, sourced from the Flan collection. Each dataset has its own format for ground truth, and we investigate both the original ground truth and the reasoning paths provided. Additionally, we explore further reasoning paths generated by GPT-4o. Section Summary. In this section, we analyze the overall dynamic characteristics of gradient differences across layers in large language models, LLMs, using metrics like the mean absolute difference, MAD, and relative difference, ROD, to quantify fluctuations and changes. We investigate gradients from 10 models across various datasets, focusing on math and common sense reasoning tasks, while also exploring the effects of different reasoning processes. Section: Wiki Knowledge Learning. In this section, we explore how large language models, LLMs, learn from knowledge-intensive tasks without reasoning. We categorize Wikipedia articles into 2 groups, popular and unpopular, based on their page views in 2021. Using a tool from Wikimedia, we extract the first 100, 500, and 1,000 tokens from each article for our experiments, ensuring we respect paragraph boundaries. For unpopular articles, we select the least viewed ones, taking the full text unless it exceeds 1024 tokens, in which case we truncate it at sentence boundaries. Next, we focus on tasks involving reasoning, specifically in math and common sense reasoning. We examine how LLMs behave when learning responses that include reasoning steps, referred to as chain of thought, COT, paths. In the math dataset, the original responses already include the necessary steps, which we call the simplified COT setting. For other datasets, we provide both direct answers and short COT paths, labeled as non-COT and simplified COT settings. This helps us analyze how LLMs learn with or without COT, potentially highlighting the benefits of COT training. We also prompt GPT-4 to create more detailed reasoning paths, which we label as detailed COT, to compare the effects of different reasoning approaches. Our findings show that when LLMs lack COT paths, they exhibit significant fluctuations in gradient scales, indicating instability during training. However, when COT paths are provided, especially detailed ones, these fluctuations decrease, suggesting that LLMs can better align their learning with the responses. We then investigate how LLMs learn correct versus irrelevant responses with different reasoning paths. For datasets with clear correct answers, we analyze gradient behaviors across 3 settings: non-COT, simplified COT, and detailed COT. In the non-COT setting, we shuffle answers to ensure incorrect responses. In the other settings, we shuffle individual sentences within COT paths, maintaining logical completeness but disrupting their relationships. Our experiments aim to see if LLMs can recognize irrelevant responses during training, as indicated by their gradient behaviors. Visualizations show that without COT paths, the gradient behaviors for learning correct and incorrect responses are nearly identical, suggesting LLMs struggle to map questions to answers without explicit reasoning. Conversely, when detailed COT paths are included, the gradients differ significantly, indicating that LLMs can recognize conflicts with their internal knowledge and require more effort to adapt to incorrect responses. Finally, we examine whether specific layers in the LLMs are more sensitive to irrelevant knowledge, as reflected in the differences between gradients for correct and incorrect responses. Our results indicate that earlier layers are more responsive to nonsense responses, highlighting their potential role in processing irrelevant information. Section Summary. In this section, we explore how large language models, LLMs, learn from knowledge-intensive tasks, particularly focusing on the impact of reasoning paths, chain of thought, COT, on their gradient behaviors when processing correct versus irrelevant responses. Our findings indicate that providing detailed COT paths enhances LLM's ability to discern and adapt to conflicting information, leading to more stable training compared to scenarios without explicit reasoning guidance. Section: Effect of Initial Models. In this section, we compare how gradients behave in pre-trained base LLMs versus aligned instructed LLMs. For each instructed LLM, we use the official conversation templates to avoid misalignment. Our experiments show that instructed LLMs do not significantly outperform base LLMs in identifying irrelevant responses, as indicated by the small differences in their gradient curves. However, we notice that while both types of LLMs exhibit smoother and smaller gradients with detailed reasoning paths, there is a notable difference in gradients for simplified reasoning paths. This suggests that instructed LLMs require more effort to learn these simplified paths compared to pre-trained LLMs. This could imply that the distribution of simplified responses differs from the instruction datasets used for training, and that gradient behaviors might help us understand how well a data sample aligns with the LLM's internal knowledge, which could be useful for ongoing training. Next, we explore the impact of response length and popularity on knowledge-intensive tasks. The left 3 columns in our figure show scenarios where LLMs learn popular knowledge with varying response lengths, while the right column focuses on unpopular knowledge. We find that response lengths do not influence gradient scales or fluctuations for popular knowledge, which contrasts with reasoning tasks where detailed reasoning significantly reduces these metrics. This suggests that the effects of detailed reasoning are due to the reasoning process itself, not just longer responses. Conversely, when learning unpopular knowledge, we see a marked increase in gradient scales and fluctuations, indicating that LLMs exert more effort to grasp this less common knowledge, which is understandable since popular knowledge is more frequently encountered across diverse sources. Finally, we examine the differences in curves when LLMs learn correct versus nonsensical responses. The nearly identical curves for pre-trained LLMs indicate they struggle to identify nonsensical knowledge, and the same is true for instructed LLMs. This differs from our findings in reasoning tasks, where LLMs can recognize nonsensical reasoning paths through increased gradient scales and fluctuations. Notably, we observe a consistent rise in gradient scales and fluctuations for instructed LLMs, especially with unpopular knowledge, suggesting that it is more challenging for them to learn new or less familiar information that wasn't well covered during pre-training.